Hey everybody, this is Miss Peachy from your WCA physical science class, and as I promised a few of you in class today, I am going to be doing a short video tutorial because we didn't get a chance to talk about covalent bonding at all, and you have a quiz on it tomorrow, and I want to make sure that we have time to kind of go through a little bit about it today. I just wanted to say happy Halloween to everybody. So, let's see here. So far we've covered ionic bonding in class, and remember that ionic bonding is where a metal and a non-metal, so a positive ion and a negative ion join together because they have opposite charges. Okay? A covalent bond, also known as a molecular bond, is where two elements bond together that are of the same charge often, and they are sharing electrons rather than trading. So remember, for example, with ionic bonds, like lithium will get rid of their one extra electron, so it becomes positively charged. Chlorine takes that extra electron, so it's negatively charged. So they actually donate or gain electrons. With covalent bonding, there's no donating or gaining. They just share electrons with each other. We still need to satisfy what's known as that rule of Octet, that magic 8 rule. Remember, the magic 8 rule is basically where an element or an atom wants to have a full set of 8 electrons in that valence shell, that outermost shell. That is when it is the most stable and the most happy. So we call that the magic 8 rule, or the rule of Octet, or I say 8 is great, but that's very important. In order for ions to do this with ionic compounds, if I go back a slide here, let me show you the periodic table real quick here. In order for like lithium to do this, for example, remember lithium has normally lithium would have 3 protons and 3 electrons. 1, 2, 3. And this is actually not the best example. Let me actually do a different one. Lithium is a bit of an exception to the octet rule. So let's do sodium instead. We'll just go one more down. Okay. So in order for sodium to do this, so sodium has 11 protons, 11 neutrons in the nucleus, and then 11 electrons, right? 2 of those electrons are in that first energy level. Oops. Got a little bit wonky there. And then we can put 8 here. 1, 2, 3, 4, 5, 6, 7, 8. That gives us a total of 10. But then it's got one more that has to go up to the next level. Okay? So it's got that one extra one that's just sitting up there in the third energy level, and it doesn't want that one. That makes it incredibly unstable, incredibly reactive. So if it gets rid of this guy, it now has 8 in its outermost shell. Now its outermost shell is shell 2 instead of shell 3. And it now has a full set of 8, so it's super duper happy. But by getting rid of the 1, it now has only 10 electrons and 11 protons, so it ends up with a positive 1 charge. Okay, so that's what we mean by that rule of Octet. It wants that 8 in there. Covalent substances also want the 8, but rather than just getting rid of electrons or gaining electrons, they share electrons when they bond together. So we're going to look at kind of how that happens. How do they share electrons? They have, a lot of times covalent substances are nonmetals. For example, like carbon dioxide is a covalently bonded molecule. Carbon is a nonmetal. Oxygen's a nonmetal. So generally, you know, they would have like charges, so they can't really bond together if they're ions. So they kind of circumvent that whole problem by sharing electrons rather than becoming charged. We'll talk about that in a minute here. Some of the properties of covalent substances, they tend to have lower melting points. They're not as electrically conductive. They tend to be more brittle. Oftentimes they're gases. Okay. Here we can see here some of the differences, right? All right, so let's look at how this actually works. So here we have a picture showing you hydrogen, right? Each hydrogen has an individual electron. Now hydrogen is a bit of a funky one. Hydrogen, helium, lithium. Hydrogen, that first energy level, only holds 2 electrons. So hydrogen doesn't need 8. It only needs the 2 to be stable. Because that first shell, the maximum capacity of electrons is 2. So it's kind of an exception here, but it's just such a small atom. So it only needs 2 for hydrogen. The rest of them will need 8. Okay? So when we see hydrogen, by itself it only has 1, so it's unstable. But if it bonds with another hydrogen, it now has 2 here, so it can be stable. Okay? And it shares those 2. So each one doesn't get its own 2. Each one only has 1, but together they can share those 2. So they'll have 8. A lot of these types of, like fluorine, for example, it bonds together with another fluorine to form fluorine gas. Fluorine has 7. The other fluorine has 7. But together, they each have access to 8. So this fluorine can take that 8. This fluorine can take that 8. So as long as they each have access to 8 electrons, it's considered to be a stable compound or a stable molecule here. Okay? Let's look at how we do this and how we kind of create these structures. Let's first talk about something called electronegativity. So something that's very, very electrically negative really, really wants electrons. Okay? Fluorine is the most electrically negative element on the periodic table. It really, 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 really wants electrons. It has 7 in its valence shell. It only needs 1 electron to be completely full, to have that full octet, to have the magic 8 number, right? Fluorine's also super duper reactive. So the combination of having such high reactivity and having only 1 electron that's needed to make its valence set complete makes it exceptionally electrically negative. Down here, francium is the opposite. Francium has 1. It doesn't want it. It really, really, really doesn't want electrons. So it's the complete opposite. So it's the least electrically negative element on the periodic table. That becomes important because it goes into the rules of making covalent molecules here. So here are our rules for trying to draw these covalent compounds. Let me just go back a slide. First thing I want to show you in this picture here are something called Lewis dot structures. Okay, so here we have every single one on here, every single element on here you can see, right? Every single one here. See how each one in column 1 has a single dot, and each one in column 2 has 2 dots, 3 dots, 4 dots, 5, 6, 7, and 8. That corresponds to the number of valence electrons for each one. Lithium has 1 valence electron right here. Beryllium has 2. Remember we did this earlier. We wrote the number of valence electrons at the top of the screen. 1, 2, 3, 4, 5, 6, 7. Oh. Yeah, that didn't work. 8 up here, okay? We wrote that at the top of the screen. We did that earlier in class, when you guys were in class. So a Lewis dot structure is basically just the element symbol and the number of dots to represent how many valence electrons there are. When you make a compound, you can create a whole Lewis dot structure where now you put those things together. And that's what we're going to be doing in the upcoming slides. Okay, so we're drawing Lewis dot structures for molecules. CCl4 here. Carbon chloride. Carbon tetrachloride. Right here. Okay. So, let me get my picture out of the way. So the first rule, it says, step 1, arrange the atoms. Central atom has the lowest electronegativity. Okay? I say, for me, a good kind of rule of thumb here means it's the furthest away from fluorine, the central atom. You've got 4 atoms here. You've got a carbon and 4 chlorines. Remember that that little subscript form tells you how many you have of that element. 1 carbon, 4 chlorines. If I look at those 2 elements here, carbon's here, fluorine is here. So the central atom is the furthest away from fluorine, which is carbon. So I'll write here carbon in the middle, and I'm going to surround it by my 4 chlorines. Okay? So that's the first step. The second step says add the valence electrons of all the atoms up. Okay. So now, I'm going to remember that there's 1 in this column, 2 here, 3, 4, 5, 6, 7, and 8. Okay, I'm going to remember that. Carbon has 4. Chlorine has 7. So I have to add all of those up. 7 plus 7 plus 7 plus 7 plus 4. 28 plus 4 is 32. So there's 32 total electrons here. Really poorly written 32. Let me try that again. Okay. Okay, better. Sometimes my tablet isn't the bestest, but so 32 total electrons. Now we're going to arrange the electrons around here to create, try to get like the octet rule satisfied for every element. Each one of these guys, each one, chlorine, carbon, they all need access to 8 electrons. So we have to figure out, how do we do that? How do we get them all access to 8 electrons? They don't need more than 8. They can't have more than 8. They can only have 8. Okay, so I'm going to start by just drawing electrons. Every time you put 2 electrons together like this represents a single bond. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. This actually worked out just perfect. Okay? So when I look at this, I have to decide, do all of them have access to 8 electrons? Our carbon has these 8. Each chlorine has its own set of 8. No more, no less. Okay? So that tells me that, oops, that tells me that that one's correct. I don't know what happened with my connection there, but reset it a little bit. Let me redraw those dots. Okay, well now that I know that works, I can draw my final picture. Okay, I'm going to put a little bit more space down here. I'm going to get rid of this. So drawing the final picture is basically just drawing what we just did. The carbon, I don't like that, it's too fat. The carbon, right, with my chlorines around it. And every time there's two dots between them, like these two here, that's a single bond. So there's one single bond, single bond, single bond, single bond. You don't need to represent these unbonded electrons over here, okay? The ones that are between the two, between the carbon and the chlorine, like here, that's one single bond. But the ones that are kind of on the outside of the chlorine ones, those are unbonded. We don't need to draw them. So our final should look like this guy here. Okay? Carbon tetrachloride. Okay, let's do another one. Carbon Die Sulphide. Kind of giving you a clue into the naming rules here too, because we haven't done that yet. Okay, so again, arrange the atoms, the lowest electronegativity in the center. Carbon is further away from fluorine than sulfur is. Sulfur is right here, carbon's all the way over here. So carbon's in the center. Kind of, you know, most of the time, the one that's all by itself is in the center, and the one that has more than one is going to be around it, right? So we have one carbon, two sulfurs. I'm going to arrange carbon in the center of my two sulfurs. Second thing, add up the valence electrons of every one. I'll rewrite these up here just for ease of use. We have 1, 2, 3, 4, 5, 6, 7, 8. Now do you guys see why it would be nice to have your own periodic table with all of this stuff already written on it like I do? I don't have to keep rewriting it every single time. I can just reference my periodic table. Okay. So carbon, 4 valence electrons. Sulfur, 6. And there's 2 of them. So add those up. 4 plus 6 plus 6. 12 plus 6 is 16, right? Now we're going to arrange them around. Remember, we want to make sure that carbon has access to 8, that sulfurs, each one have access to 8 to satisfy our rule of octet. So I can start here, and I can draw them like this if you want to, because that makes it look more like a bond, but it doesn't really matter. So 1, 2, 3, 4. We need 16 total, right? So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ooh, I have a problem. I have a problem because right now, each one of my sulfurs has access to 8, which is good, right? But my carbon only has 4, so carbon's going to be kind of mad about that. Carbon needs 8 too, otherwise it's not going to work. So if you encounter that situation, that's your clue to move some of your dots. What I can actually do is I can take these dots and put them like this. And it looks weird. But if I look at it, sulfur has 1, 2, 3, 4, 5, 6, 7, 8. The sulfur has 1, 2, 3, 4, 5, 6, 7, 8. And this carbon has 1, 2, 3, 4, 5, 6, 7, 8. Everybody has 8. It's not pretty, but everybody has access to 8 electrons each. Notice now that there are 2 sets of 2 between the carbon and the sulfur. Each 2 represents a single bond, so 2 sets of 2 represents a double bond. So how you would draw this is you would actually draw this as 2, or a double bond here and a double bond there. 2 lines. That's what it looks like. Remember, you don't need to draw those extra dots out here. Those are not necessary to draw. You only need to draw the bonded electrons. So your compound looks like that. Carbon disulphide. Okay? They're sharing those electrons, but they're still satisfying that magic 8 rule, that rule of octet. Okay. Now we've talked about, I've kind of alluded to the fact that these have names that are a little bit different than you did for ionic compounds. Remember, for ionic compounds, you did the full name of the positive ion, and then the negative ion, you dropped the ending and added IDE. You're still doing the same thing, but now you are using prefixes to represent how many you have of each. Okay? These are the prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Those represent how many you have of each. So you use this for both the first and second position. So both the positive and negative ions you will use the prefixes for, with the exception, there's always an exception, if mono is in the first position, we don't say mono. So NO is nitrogen monoxide, not monooxygen monoxide, okay? Or mononitrogen monoxide. It's the only exception. If mono is in the first position, we drop it. But here we have N2O3, dinitrogen trioxide. N2O3 dinitrogen trioxide. So we do use the prefix for the first position and the second position, with the exception of mono in the first position. You still drop the ending and add IDE. You're not saying dinitrogen trioxygen. You're saying dinitrogen trioxide. Okay, so remember that part too. Okay? Okay. So some examples here. We would say hydrogen monofluoride for the first one, HF. Hydrogen monofluoride. Number 2, what do you think it would be? Think about it for a second. Pause me. See if you can say it to yourself. It would be dihydrogen monosulfide. Dihydrogen monosulfide. Number 3, nitrogen monoxide, or nitrogen monoxide. We don't want to say monoxide, it's a monoxide. Number 4, dinitrogen monoxide. Number 5, nitrogen dioxide. Number 6, dinitrogen pentaoxide. So the reason why we have to do this for covalent compounds and we didn't for ionics is there's so many different combinations. For ionic compounds, there really was only like one way they went together, right? Nitrogen and oxygen obviously are going together in multiple ways. So we can't call them all nitrogen oxides, or you would have no idea which one we're talking about. So we need to use those prefixes to be specific. It's very important in that way to be communicative. Okay? All right, see if you can do the other ones on your own. If you can do the other ones on your own, practice those a little bit. So the 2 things we did today in this video is you learned how to draw Lewis dot structures, single bonds, double bonds. We didn't do triple bonds, but they're there too. So if, for example, you had, let me do one real quick here. Let's do... Let's do oxygen. No, not oxygen. One second. Okay, sorry, oxygen's double bonded. We'll do nitrogen. Nitrogen is a good example. So nitrogen is N2. And we're doing 2 nitrogen atoms. There's no central atom because there's only 2 of them. Let's look at the number of valence electrons for each. 5. So 5 and 5, 10 total. So we got to divvy these up so they each have access to 8, remember. And just to save us a lot of time here, the way this ends up working is if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. That's the only way they each have access to 8 of them. Okay, you can see 6, 7, 8 for nitrogen here, 6, 7, 8 for nitrogen here. So we would draw this, since there's 3 pairs in there, with 3 bonds, a triple bond. So you can have triple bonds as well. Single bonds, double bonds, and triple bonds. So there's a lot of different ways that these guys can go together. And because there's lots of different ways that they can go together, lots of different arrangements, then we have to use those prefixes. The mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, to be able to make sure we're really being very specific and communicating well. Okay? All right. Well, if you have any more questions on that, let me know. You do have a quiz on this, like I said, coming up tomorrow, but you also have a portfolio on this stuff next week as well. So hopefully that all helps out a little bit. I know it's a little bit of a long video, but like I said, this stuff's kind of difficult, so I want to make sure you have the instruction that you need. And have a fabulous day, and happy Halloween, everybody.